All right. So we have done some preliminary work. So first of all, per our graph, okay, per our graph, I'll use red ink. On the per our graph, which is actually like this. And this one we say is horizontal. And this one we say is vertical. This side contains 10 big boxes. And this one contains 12 big boxes. And every big box, contains 10 small boxes. So this one to note it. I think let me increase the percent here so that okay. Now let's start. So what are we going to do now? Determination of scale. Okay. So step 1, calculate change in X. We should note that in our case, because the load is plotted on the vertical, the load here is the Y and the extension is the X. So let us take note of that first. I will tell you that, first of all, calculate change in X. Okay. So note that X is the load. Okay. X is the load. Okay. Oh, sorry. X is what? Extension axis. So take note of that. Let me move it a little bit up and then we can have space to work. So here, this is what we're going to do. Calculate change in X. So change in X is equal to maximum value minus minimum all over sorry, hold on for me. Change in X is maximum over minimum minus minimum. Okay. So in that case, we have noted from the graph that our minimum for the extension is 0, and then our maximum is 5.85. I also want to let you know that even if you don't have 0, it is safe to use 0 as your minimum. Otherwise, your graph may go beyond the scale you may be choosing. So the maximum is 5.85 and the minimum is 0. And this will give us 5.85. So that's the first thing. So step 2. So let us know that now we are dealing with the x direction. So step 2. Calculate lower bound value. Can I even call it LBV? Let me call it LBV for short. So lower bound value is equal to the LBV is simply equal to change in x over number of boxes. Let me go back here. Number of boxes. Number of boxes in x direction. Okay. Somebody's hand is already up. Yes, Joseph.
Good morning, sir.
Good morning.
Please, can you restart the determination of the maximum value?
Are you now joining?
No, sir. I've been with you
Since how many minutes now?
since the beginning.
And you don't know what is maximum. I don't agree you were here from the beginning. I will not answer your question. Let's proceed. Okay. So lower bound value is changing x over number of boxes in x direction. Someone else. Shadrach.
Sir, good morning.
Good morning.
Please, sir, last time you told us, if we are doing the graph, because of the curve, if you do it maybe a straight like the way you do them now, you'll get it small one. So we should turn the graph.
No,
Please,
hold
can we
on,
turn?
hold on. We are here together. So allow me to go. Whatever question, I'll address it. Okay, but let me finish it first, please.
Okay,
That's
sir.
the
Thank
way
you.
we learn. Okay. Now, looking at the way our graph is, okay? Looking at the way let me tell you, originally this is how the graph should look like, and then you have something here, you have a place here to write your name and all that, okay? But there's no hard rule that the graph cannot be turned. Looking at the way our graph behaves, it will be better for us if we turn the graph this way. If the graph sheet is turned this way, we'll get a better graph. And so note that we'll turn the graph this way instead of this way. So if we turn it this way, our x-axis will now be the vertical, and our y-axis will now be the horizontal. Is that right? So in this case, note that our x-axis now will have 12 boxes. Okay? That will have 12 boxes. Um, um, I don't even know what to do now. Okay. So now I'm going up. So to make life easier, I'm going to change. I'm going to change number of boxes now to a different, so that there will be no confusion. So large squares. In the X direction, okay? In the X direction. So in this case, now that I told you that we are turning the graph this way, this is now our X, and this is our Y. This one has 12 boxes, and this one have, I can still, in this one, then the vertical will now have 10 large boxes or squares. Okay? So in this case, when we divided, we had 5.85. So 5.85 divided by 12. Now it will be 12. And this will give us what? 5.85. 5.85 divided by 12. This will give us 0.4875. Okay. Step 3. Calculate upper bound value. So let me call it upper bound value, UBV. Let me call it that way for short. Let me move up. So if you are calculating the upper bound value, it's very simple. It's very simple. The formula, upper bound value, is simply equal to lower bound value times 2. This is the formula you use, okay? So it means the lower bound value is 0.4875 times 2. And this will give us 0.975. Okay? Then, okay, people are also calculating alongside. So step 4. Step 4. Interval. The interval now is upper bound value is lower bound value mapping onto upper bound value. So the interval, okay, is equal to 0.4875 to 0.975. Then what is the last thing we'll do? Which I'll call it step 5. This thing is just a simple minute. Within under less than 1 minute, you'll be able to do this. But because I'm teaching, it will be a bit longer. Step 5. Choose scale. Note. So if you are choosing the scale, choose suitable. Okay, do I even need to write it there? That would be. So the fifth one, choose scale. Okay. So note, choose suitable value from the interval. And then the second thing is that selected value should be easily divisible. Am I even right with my spelling? Should be easily divisible by 10. All that we are saying is that now, let's see what this interval here now means. The interval here now is that now you have all the way from 0.4875 all the way to 0.975. So any value within this can be used. Okay. So if you want to, from here 0.4, I can have 0.5, 0.6, 0.7, 0.8, 0.9. Okay. So you make sure that the smallest number here should be 0.4875. And this one should be 0.975. So any value within this can be selected. But what we are saying is that try to select a value that is easily divisible by 10. So don't go and select 0.605. No, just choose a reasonable value within this interval. So this one, somebody will say you choose 0.5, 0.6, 0.7. But if you choose something within the middle, is the best option. This small one here will give you the biggest graph. And this big value will give you the smallest graph. So choosing anything within this interval is fine. So I would say that, why don't we choose this? Well, somebody else may choose this, whichever. That's okay. Okay? So this one is for the exercises. Any question on this? So now our scale. Our scale now is that 2 centimeters is equal to 0.8. The extension is millimeters. So this is now our scale. Let me move up a bit. Like I told you, that big box, the last square is 2 centimeters. The large square is 2 centimeters. So take note of that one. All right, so this is now going to be our scale for the extension axis. Any question? This one you can even, you don't need to even write it. You can, it's just a rough work. You don't need to show this when you are drawing the graph. No, it's just a rough work. Okay. Any question? Any question? If you have a question, raise your hand and I'll help you. Okay. Now that everybody is cool, let's look at the y-axis, okay? So this is for the x-axis. Let's look at the y-axis. Y-axis. And remember, the y-axis represents our load. The y-axis is the load axis. So step 1, calculate change in y. So change in y is equal to maximum value minus minimum value. This one was determined right from the beginning, okay? So if we go to our graph like this, from the load, we know minimum is 0. And if you look through it, we know the maximum is 261 or so, we saw. The maximum value is 261. So that's what we are going to use now, okay? All right. I also want to say that even if you don't see 0, it's safe to use 0 as your minimum so that you can get a very good scale. So it's equal to 261 minus 0. And this is 261. Step 2. Calculate lower bound value, LBV. So what is the lower bound value? So LBV is equal to change in y over number of large squares in y direction, okay? Our change is 261. Per the way we turn our graph now, this side now is 10 boxes. 10, okay? So this will give us what? 26.1, okay? This will give us 26.1. Let's proceed. Step 3. Calculate upper bound value, which I'll call UBV, okay? So upper bound value is equal to lower bound value times 2. You always multiply the lower bound by 2, and then you get your upper bound. So which is 26.1 times 2. 26.1 times 2, 52.2. 0.2, okay? Okay, so I'm seeing all those who just joined is their business. So it's your business. This is a tutorial session, so you need to make yourself available. Step 4, interval. The interval now is lower bound value mapping onto upper bound value. So this is 26.1 to all right, sorry, I paused the video a while. Okay. All right. So the interval now will be 261 to 52.2. Okay, now step 5. Choose scale. And I said the scale must be chosen between the interval. Okay, so the lower, so this is 26.1. And this is the lower bound value. If it is 26, what values can we have? Assuming we didn't want to use, we can have maybe 30, 35, 40, 45, 50, 55, 60, 8. Can you find an equal? I think it's a track. We can only go up to 50, and then the upper bound 52.2. This is the upper bound value. So essentially, any value within 26.1 to 52.2 is possible. But what you should note is that you don't want to pick any on a raw value. Pick a simple value that can be easily divided by 10 without plenty decimal places and all that. So just pick a suitable value, okay, within the interval. So in this case, somebody may decide to choose 50, somebody will choose 45, 40, 35, whatever. So it depends on you. It depends on you. So which one? Let's see. So if I choose 50, okay, let me see what people are saying in the message box. Okay, some people are choosing 40, some are choosing 50, some are choosing 45. So you see that it's a choice. It's just a choice. You decide on what to do at a point. So now where you get a final say. Me, I be teacher. Okay. Me, I be teacher. Okay, so let's say that I'm choosing 45. Okay. Let's say I'm choosing 45. Let's say I'm choosing 45. So scale. The scale now is 2 centimeters is equal to that 45 now is in kilonewton, because you should know that our values are in kilonewton. So this is now my scale for y axis. which is actually the load axis. Okay. So now, now we are finished now. Okay. Oh, 45 is easily divided by 10. Okay. When you divide 45 by 10, you get 4.5. And it's okay. We don't want you to get 0, 5, maybe 0.0000. No. Okay. That's all we don't want. Okay. Now, let me move to the top. I am not sure I remember what the scale we had for the x-axis. This is the x-axis, 2 centimeters, 0.8 millimeters. Okay. Extension axis. Okay. So we had, so now scales. X axis, which is actually the extension. We have 2 centimeters is equal to 0.8 millimeters. And then with the y axis, which is actually the load axis, we are having 2 centimeters is equal to 45 kilonewton. And all that I want to see is this. This is all that we were looking for as the first. So all that we have done so far, you can use some few minutes to have done that. Okay. You can use some few minutes to do that. And that should not take you more than 2 minutes, or let me say, it shouldn't take you more than 5 minutes to choose a skill. No way. If it goes beyond 5 minutes, it means something is at stake. Okay. Any question up to this stage? Any question? Okay. I think that everything is clear. Hanifa. Hanifa.
No one will say. Network. Sir, please. Network.
So I'm listening.
Sir, please, when you are being given the question, is it compulsory to calculate all this?
I said this is rough work. Whichever way you use to get it, it's fine. I don't even want to see this working anywhere. I don't need it. Right? Do you get it?
Yes, sir.
Don't show this working anywhere. It's just a rough work to help you get your skill. You can simply use calculator without even writing anywhere. I don't want to see any writing anywhere. All I want to see is the skill. That's all. Is that okay?
Yes, sir.
Okay. I'm repeating this. I said, this is rough work. You should not even use 5 minutes to do this work. You don't need 5 minutes for this work. All that we're looking for is this, a skill for the X and a skill for the Y. Okay? Let's look at Now I've got my scale. Let's look at the plotting. Now let's look at the extension axis, and which we have a scale of 2 centimeter is equal to 0.8 millimeters. Note that the 2 centimeter is one large square containing 10 small boxes. Are we okay? I hope we check this from the beginning. That the big box we use, how many small boxes are in one? I still want to know. Maybe if some people cannot recognize that. The big boxes. Okay, now if you remember, then that's fine. We all noted that every big box contains, every big box contains 10 small boxes. So I will tell you that plot the graph with boxes rather than the numbers. So what do? Value, calculate value, per box. If you want to know the value per box, then this is 0.8 millimeter. Divide this one by 10. Okay, this is a number of boxes. So this 10 is the number of small boxes. Okay, and this will give you what? 8 divided by 10 will give me 0.8. 0.8 divided by 10. This is 0.08 millimeters per box. And this is what you need for plotting. Okay, this is what that you need for plotting. I'll show you why. Plotting with boxes is more important than plotting with the actual numbers. Okay, good. Can we do the same for the y? Let's do the same for the y. Okay, load axis. Load axis. What was our scale? 2 centimeters is equal to 45 kilonewton. So value per box is simply equal to our 45. So 45 kilonewton divided by number of small boxes per 2 centimeter. Everywhere is 10. So this will be 4.5 kilonewton per box. So here, in simple terms, one small box is equal to 0.08 millimeters. And this one to one small box is equal to 4.5 kilonewton. Let us take note of this. Any confusion? Any question? I'm saying we will plot with boxes rather than So when you plot with boxes, your graph is more accurate. Okay. Any questions so far? Can anybody do this? Okay. Now we are going to plot our graph. So I'm going to pull my graph sheet that was shared by my able computer lizard. Okay. All right. It's good I have a very powerful graph, and I thank this gentleman for showing me the level. Okay, I'll put this one aside, and I'll increase my graph considerably so that all of us, we can see exactly what is going on. I still want to increase it. Oh, me refi me ho koraa. Me a efi me ho ne say. So first of all, hey, madi ntumi enye ketewa kakra ma me. Wow. Okay. So first of all, I think I have to turn my graph. I have to rotate it. Can I rotate? I can say a very rotate you here. Let me go and rotate it in my document before the worst case scenario. Okay. Now I rotate them. Okay, so this is what we are going to do. So first of all, the scale we choose is that for the low axis, you can have it this way. You see, when you are plotting graph, you have to use a lot of discretion to do many things. If this space, if there's no space here, you have to go in a bit, one box above, so that you can have space for your graph. If you don't have space to write, you need to do some pattern, right? So let me say that I am jumping up here so that this one is 0. So this is the extension axis. So if this is the extension, my interval is 0.8. So the first one is 0.8. This one is 0.8. In multiples of that, so 0.8 times 0.8 plus 0.8. This will be 1.6. If I add plus 0.8, I'll get this to be 2.4. Again, I'll get 3.2. I'll get 6.0. I'll get 4.8. I'll get 5.6. I'll get 6.4. I think my graph is a bit bigger, so don't be worried at all. So now this is the origin once again. So I go here, I have to have this now my load as this. I told you should have your a graph sheet, so I suppose that you have yours. So on the load as this, we said is 2 centimeters equal to 45. So this is 0. This will be 45. I'll add 45. That is the interval. This will be 90. This will be 135. This will be 180. This will be 225. This will be 270. Okay, because we had up to 261. So enough. So this line must be drawn. Okay. This is the extension. And this has to be written mm. And this one is load. Then you write kn. Okay. Now this is what I expect from you. I'm not too sure if I intend to enlarge my graph, what will happen to me here? I can't tell unless I try. Hey, Charlie, the thing they move plus my writing. Quick. Wonderful. So life make easy. Life make easy work. Quick. Okay. So you have to draw your line. I expect you to draw this line. Where is my ruler? I expect you to draw this line. You have to use your pen or whatever pencil you are having to draw this. So I will draw this. Let me move up a little bit. Okay. I'm rotating to 0. This one too, I expect you to draw this line. I expect you to draw this line. Good. You see at the abuano. So you have to draw this line. Now that you are through with this, let us now start plotting. Any question up to this stage? Any question? Any question? Yes, at the back.
Sir, please, I have no idea concerning the load extension graph, so I wanted help with it.
In fact, today my intention is not to teach about the basics of load extension curve. So it means that you have to revisit some of our videos. Okay.
Okay, sir.
All right.
All right. Thank you, sir.
Okay. Any questions so far? I have some few minutes to leave for a meeting. Any questions so far? Okay, then let's proceed. So now, what do we do? Easy. Now we know the value of one box in the x direction. We also know the value of one box in the y direction. So here, I only have to enlarge my graph whilst we are about to plot. I still want to make it bigger. I still want to make it bigger so that at least everybody can see. Good. Okay, now let's plot now. So from the question, let's start with when we are plotting, you plot the load and the extension at a go. So the first point, I'm going to use maybe a black color. The first point is 0, load is 0, extension is 0. So it's here. Okay. The second point, load is 20, extension is 0.05. Anytime you take a load value, you divide by this. If you take extension, you divide by this. Please, Richmond, hold on for me. So if I take 20, I told you I'm using this question, so I suppose you have the question. The next point is now 20, load is 20, extension is 0.05. So if you want to get a excuse me. If you want to get the extension, take the value there and divide by 0.08. Okay? So in this case, for the extension, so extension Control Z. As for some people, I know that they will ask when your value no way. But maybe when my team have a pancophony, this is the load, and this is the extension. This is the original question. The first point is 0, 0. The second point is 20 and 0.05. The next point is 40. Then we have 0.10. The next point is 60. And then we have 0.16. And so on. The values are there. Okay. So the first point, load is 0, extension is 0. The second point, extension is 0.05, and then load is 20. So if I am plotting the extension, every value I take, I'll divide it by 0.08, this one. If I pick any load value, I'll divide it by this one. So let's go. So 0.05, if I divide it by 0.08, 0.05. 0.05. If I divide it by 0.08, what do I get? Point 0.08. 0.625. and this is boxes, okay? So I'm getting 0.625 boxes. That's about 0.6 boxes. We know this is one box. So I think I need a thinner pencil. Okay, I can equally show you here. This is it. This is box, box, box. This one from here to here is one box. The middle of the box is 0.5 and so forth. So you can find 0.1, 0.2 within one box. So the answers you'll be getting, they are in boxes. So 0.625 is less than one box. It's just about half, somewhere beyond the half of a box. So here, I'll just locate somewhere beyond half of the box here like this. The load, let's divide the load by 4.5. So 20 divided by 4.5 is 4.444. So the answer is 4.4 boxes. So on this axis, I'll go 1 box, 2, 3, and 1, 2, 3, and this is 4. So 4.4 is less than 6. So somewhere in the middle there, I can have this point. Don't worry. Let's go to the next point. If I go to this now, 40 and 0.1. So the 0.1, when I take it, I divide by this. Always divide by this. So if I divide 0.1 by 0.08, 0.1 divided by 0.08, 1.25. 1.25. So it means one box, one full box, and then 0.25. So 1.25 boxes. So this is one box. This is 2. So somewhere here in the middle, 1.25 in the middle between 1 and 2. Less than half a box. Then if you divide the load, 40 divided by 4.5, you get 8.88 boxes. So let's say 8.9 boxes. You should know that from the 0 to here is 10 boxes. So 8 will be somewhere here. So 8 point something will be here. Okay? I want bigger values so that it will be easy. Let's look at the 60. 60 divided by 4.5 will give us 60 divided by 4.5. 13.333. And then 0.16 divided by 4.5 will give us 0.16 divided by 0.08. 1.75. So here we have the x-axis, we have one box, two box. So it's still within the second box, 0.75, okay? 1.75 boxes. So this is the first box. This is the 0.75, let's say it's here. And then this one, when divided, we had 13.33. We know up to here is 10 box. From here to here is 10 box. 11, 12, 13. Maybe 0.33 somewhere here. Okay. Then this one to our plot. So let me see what message people are giving here. Okay. So what is the easiest way you can go around it? I will say that on your paper, pick each of the load values and divide it by 4.5 and write them on top of them. Okay. And then pick each of the extension values, divide it by 0.08 and write the answers on top. Okay? So I want the one that can be more significant and then people may understand. I'm picking, now I want to pick, I want to pick I want to pick 250 and then 2.51. I want to pick these two values now. So if I divide 250 by 4.5, 250 divided by 4.5, I'll get 55.56 boxes. Then if I take the 2.51, I'll divide it by 0.08. What do I get? 31.375. I repeat again. When you divide by either 0.08 or 4.5, the answers you get are boxes. Please, they are boxes. So this one with the X value, I have 31.325 boxes. This 0.3 is less than half a box. So 31 boxes always counts from the origin. From the origin, I know up to here is 10 box. This is 10. This is 10, making 30. Now 31. And then 0.32 is less than 0.5. So somewhere here, okay? Somewhere there. Let's look at the load, 55.56 boxes. We know this is 10, this is 10, this is 10, this is 10, making 40. So it means I have to move up a little bit. So 51 point something, eh? 55.55. So this is 10, 10, 30, 40, 50, right? So this is 50. 50 is here, 50 boxes is here. Then 5. 1, 2, 3, 4, 5. 5 is here. 0.55. That's less than a box, okay? So maybe here. So I trace this point. Where is it? This point. This point all the way here. All the way here. Okay. So now this point I'll take. Please, all this dotted line is not necessary. But where the 2 points meet, I'm going to do it that way. So you do this for all of them. And then after you finish the points, the graph will show you clearly. And then you draw. So let me move up a little bit. Okay. So this is how you are going to go around it to plot all the points. And when you finish, you note that from the beginning up to a certain point, when you put your ruler, you can draw a straight line. Then you now draw that straight line, and the remaining part connect with a smooth curve. And then that be it. Asafo.
Sir, please, I wanted to make a correction for 0.60 load and the extension is 0.16.
Point what?
So please put 0.16. When you divide 0.16 by 0.08, you are going to get two boxes.
Oh, are you sure?
Says
0.16 divided by 0.08. You are right. You are right. Thank you very much.
thank
Yeah.
you're welcome.
Any question? Any question? So this is the you see, okay, thank you. So let me take you up there and show you where the power lies. Now, after you have gotten the the 0.8 and 0.5, this is what I expect that you can do, and then it will make your plotting very faster. You see, with the extension, we had one box is 0.08, and then with the load, one small box is 4.5 kilonewton mm. So what I will admonish you is that pick each of these values and divide by 4.5 and write the answers. 0, 20 divided by 4.5, 4.4, 4.4. Okay, all these answers are in boxes. Okay, then pick each of these ones to and divide all by 0.08 and write the answers maybe in pencil. So when you are now plotting, with the values in the pen. That will make your plotting very faster. So which means that you will take even about 5 minutes per to plot the whole graph if you start plotting. Is that okay? So always you start counting the boxes from the origin. That's what you should note. Okay? Any question? Any question? Any question? Is that pretty easy? Okay, since everybody is quiet, I now see that everybody is okay. Everybody is fine. Because I have another meeting, let me quickly touch on some few parameters on the graph, and then I can go in peace, but not in pieces. Okay. The way people are quiet, I see that this graph, they can now plot it. And I have to get some Kimpiski fried rice and some more. If you don't know where the Kimpiski is coming from, one of my senior friends who showed me how to enjoy strength. Yes, if you get some Kimpiski fried rice and a chilled malt, oh God, you can do strength the whole day while you know that you are working crumple. Okay, Yeah, no. Okay, so let me just use this some few minutes to address this matter. So this is essentially the graph we are plotting: load, Kn, extension, Mn. Please pay attention because I have just some 5 minutes to do this one. The start of the graph will be a straight line like this. And then it's going to go like this. Going to go like this. And this is a fracture. In lecture 2, the lecture note, every single formula you so require is in that lecture note. So you may have to go back to that lecture note and then get the formulas properly. When you plot your graph, it's like, so from here, 0 up to a certain point here, where the straight line ends, is your proportional limit. Where the straight line ends is your proportional limit. Where the curve actually starts, somewhere here, just above the proportional limit, just above the proportional limit, you have that place to be the elastic limit. Okay? And where the curve starts turning, where the turning starts, this point is a yield point. And when you, after you have drawn the curve like this, the highest point here, if you trace it here, the highest point here is the maximum point. So the load that you read is the maximum load from here, okay? So let's see, how do you determine the E, elastic modulus? E will be determined by E is equal to stress over strain within, you must write this as I keep saying, within elastic limit. Once it's a graph, you must indicate that. Right.
Yeah, please, is it the same as the ultimate stress, the maximum point?
The stress you calculate there is the maximum stress or ultimate stress. The point is a point.
So it's the
The
same.
point is not the stress. You understand?
Okay. Okay.
Okay, all right.
Okay, thank you.
So because this is load extension curve, please, iPhone, if you don't change your name, I'll not answer your question. I'm sorry. Who is called iPhone? Unkura na ukuta iPhone was school. Tebia iPhone was a sadino. iPhone Chinese iPhone. Charlie, make I think of myself. You have yellow card now. You this boy. Okay, so because it's load extension curve, just pick a load anywhere within the straight portion. Listen carefully. Pick a load anywhere within the straight portion. So let's say if I pick a load value here, trace it to this axis, and trace it to this axis. And you're going to have a P here, and you're going to have delta here. Okay? So now that you have done that, the change in length, the P you use here, the stress, use that. Okay? Use that is that P over the area. Okay? The area is the original area, A naught. Then the strain is equal to the change in length here, okay? The extension. Hey, what is that? The extension, which is delta L. divided by original length, which is the gauge length. After finding these two, come and put it back into this formula to evaluate your E. Okay, I said pick a value within the straight line portion, anywhere. And that's what I expect you to do. My time is against me, seriously. Daniel. Daniel, please, can you talk?
Sir, good morning.
Good morning.
Sir, please, you see the fracture. You didn't write the fracture, or that one is not part.
It's part, it's part. You know, because I'm in a
Okay.
hurry, so. Okay.
Okay. All right. Thank you very much.
This is the fracture. This is a fracture. Okay. All right. So this is how you evaluate the E. Note, I have mentioned over and over again that the slope of the load extension curve, the straight line portion, is not E. I have said it over and over again. The slope of the straight line portion of a load extension curve is not E. Okay, so if you go and calculate some slope value, I'll simply give you 0 and be smiling. Okay. So finally, my time has catch up for me. So here, like I said, the lecture 2. Okay, lecture 02. All the formulas you need inside. So this is what you do. You can evaluate the E using this approach. Then if you want to find the stress at the proportional limit, the load here, I say where the straight line ends, just trace it to this as this, and then you can find the P. You can find the load here and use the load at the proportional limit divided by original area. Okay. If you want to find the stress at the elastic limit, I say elastic limit is where the curve actually starts. Okay. And it's very close to the proportional limit. And it's when you trace this to the loader, you pick that load. So load at elastic limit divided by original area will give you stress at the proportional elastic limit. If your maximum stress or ultimate stress, the highest point as you trace here, use this load divided by the area, original area, then you get the stress at the maximum point. Okay. Please, I want to say once again, the formula for all this is in lecture 2. The slides are posted on the LMS. It's in there. I want to admonish you all to go for that slide and get all the formulas that you can use to work it out. Okay. What again? So the yield point, load at yield point divided by the area. Okay. Now, if you want to find sometimes I can say apply a factor of safety to the yield stress. If I say apply to the yield stress, you are going to use the yield stress. Okay, divided by, so factor of safety is equal to, permissible stress is equal to yield over factor of safety. Yield stress over factor of safety, or ultimate stress over factor of safety. And I'm telling you, the question may tell you, apply it to the yield stress or to the ultimate. whichever that you are given, use the appropriate formula. Okay. All right. Finally, I want to, oh my God, my time. Finally, I want to just touch or within 1 minute on the proof stress. Proof stress. I say proof stress is actually used where the material doesn't have a distinct yield point. So we use 0.2% strain for the proof stress, right? So this is strain. You cannot get strain directly on the load extension curve. So everybody know that strain is change in length over original length. We can make change in length a subject here. So change in length is equal to the strain times the original length. So the strain, this is percentage. So it's actually 0.2 divided by 100 to change it to decimal times the original length. Then you get the change in length. Okay? You get change in length. Then you come and measure here on this as this, the value you get. And then you draw a line parallel to this line like this. Wherever you cut the graph, okay, that point becomes your yield point or the proof stress. Okay, that's all. All right, that's all. So I personally believe that plotting of the graph is a major issue, but I think I've tried to address many things for this. Any question? I have a meeting, so that is why I have to try and leave because they are waiting for me. Any question? If you have any question, let me know. Any question? Any question? Any question? Okay. So I want to admonish all of you to try and plot this graph again. Okay, using the approach we have studied. This approach is universal, can be used to plot any graph in this world. And so with ease, I tell you. So please try and make sure that you plot this graph on your own and you're able to do the evaluation. If you plot and you want to send to me on WhatsApp to check for you, I will do that gladly. All right. So all right. So thank you so much, and I'll stop sharing here. And we have successfully come to the end of this tutorial. And I'll post the video in due time, but I won't post now because I'm running for a meeting. After the meeting, I'll post the video. Thank you very much, and glad to see you join. Okay. All right. So class has ended.